For years, the capability of artificial intelligence grew at a compounding, exponential rate. Now, that race has hit a ceiling. Look at the technical frontier. The models produced by Anthropic, xAI, Google, OpenAI, Alibaba, and DeepSeek have become virtually indistinguishable. This chart shows performance ratings from the ARENA leaderboard. These 6 major labs are now clustered within 25 ELO points of one another, a margin so thin it renders their differences statistically negligible. This convergence isn't limited to individual labs. The geopolitical gap between the United States and China has also effectively vanished. As of early 2026, the performance margin separating the top US and Chinese models is just 2.7%. In February 2025, DeepSeek R1 briefly matched the top US model outright, demonstrating that technical parity is no longer a future goal, but a present reality. Because these systems are achieving nearly identical results on standard tests, the era of competing purely on raw intelligence or access to compute is over. When everyone has access to the same level of superhuman reasoning, the foundation model ceases to be a competitive moat. It becomes a commodity. This creates a dangerous illusion. Developers are currently reporting scores near 100% on expert-level benchmarks, suggesting a level of reliability that isn't there. The advertised input capacity is staggering. Models can now ingest over 1 million tokens of data in a single pass. That is the equivalent of processing an entire STEM PhD thesis instantly. But inside production environments, this genius-level performance is met with bizarre basic failures on structured tasks. On the OS World benchmark, which tests whether agents can perform basic operating system operations, these systems fail roughly 1 in 3 attempts. We see high-level academic success paired with elementary errors. Gemini DeepThink won a gold medal at the Math Olympiad, but reads a basic analog clock correctly only 50% of the time. This is the Jagged Frontier, a paradox where elite capability and basic incompetence coexist unpredictably. Unlike human learning, which scales linearly, AI capability is fragmented. A model can solve a PhD-level physics problem and fail to navigate a file folder in the same minute. The models are still evolving, but our instruments for measuring that evolution are broken. Relying on these high benchmark scores to predict how a model will behave in the real world has become an active engineering hazard. The problem starts with the evaluation infrastructure itself. Recent audits suggest that the industry-standard benchmarks used to claim state-of-the-art status are structurally compromised. Evaluations designed to challenge models for years are now saturating in a matter of months, making it impossible to distinguish between top-tier competitors. These audits also revealed massive rates of invalid or broken questions within the tests themselves. Consider the GSM 8K benchmark, a primary measure of math reasoning. A review found that 42% of its questions were invalid. This technical failure is compounded by selection effect gaming, where labs iterate models specifically to climb the rankings. High leaderboard standing is increasingly a reflection of a model's adaptation to the testing platform, rather than its actual generalized capability. If the benchmarks used to define progress are mathematically compromised, the industry is navigating by a false map. We see the same pattern in context windows, the metric used to sell enterprise-grade data capacity.
Since mid-2023, the amount of text a model can physically ingest has increased by 30 times per year. As this chart shows, labs now market an accepted context window that technically allows inputs of up to 10 million tokens. But processing doesn't mean recalling. Multi-needle retrieval tests show a massive gap between what a model can accept and what it can actually understand. The usable context window, the point where a model maintains 80% accuracy, is orders of magnitude smaller than the marketing suggests. For engineers building retrieval-augmented generation pipelines, trusting these advertised limits without testing for this decay is a major reliability risk. Currently, adding more tokens is often an architectural illusion that masks shallow processing. Because models are converging at the same technical ceiling, improving them further has become a zero-sum game. There is now a direct, measurable tension between dimensions of responsible AI, specifically between safety guardrails and baseline accuracy. Empirical evidence proves that as we pull the lever to increase a model's safety, its accuracy dynamically collapses. Improving one dimension happens at the expense of the other. Under normal conditions, most frontier models receive good or very good safety ratings. However, these complex systems are highly vulnerable to adversarial jailbreaking attempts, where prompts are deliberately manipulated to bypass safety guardrails. These alignments are fragile. Under deliberate attack, safety scores for nearly every major system drop by a full tier or more. Since a flawless model is currently mathematically impossible, deploying AI means deciding which specific flaws a business is willing to accept. In the real world, theoretical benchmarks matter far less than the ability to execute a multi-step workflow. The competitive moats for builders have shifted from raw capability to cost, reliability, and domain-specific execution. We are seeing rapid progress here. AI agents have jumped from 12% to 66% accuracy on OS world tasks in a single year. But even with that leap, a 33% failure rate remains too high for unconstrained, autonomous environments. Raw intelligence is a secondary concern if the system cannot be trusted to navigate a real-world operating system without supervision. Because companies are deploying these jagged systems that benchmarks cannot accurately measure, we are seeing a shift in how work is organized. This is seniority-biased technological change. Companies are using AI for junior-level tasks while relying more heavily on senior staff to catch the model's unpredictable errors. This means entry-level workers in AI-exposed fields are absorbing the shock of displacement, while senior roles remain insulated by the need for human verification. This transition is moving faster than the public realizes. While the general population expects a slow evolution, AI experts are forecasting a much more disruptive timeline. This creates a fundamental engineering problem. If the underlying foundation models cannot be accurately measured, how do you build a system that won't fail in production? Success requires shifting focus. Builders must stop chasing the smartest base model and start engineering the most resilient, fault-tolerant architecture around it. The measurement collapse is a filter. The winners of this next wave will be those who stop trusting the broken yardsticks and start engineering for the jagged frontier.